stuff you've seen before. We're going to go through it pretty quickly, though, and then we're going to go into a little bit more depth than you would have done in college algebra and Math 121. How many of you took Math 121 here? What about, well, only about half. Less than I would have thought. All right, so for those of you that didn't take 121 here, I think most of this will be review. We'll find out. All right, so we're going to talk about functions, and we're going to talk about the properties of a function. And some of the basics, when we think about a function, we're thinking about it as a set of points that passes the vertical line test, right? That's our basic idea of a function. Set of points in the plane, passes the vertical line test. And some characteristics that we are going to talk about: increasing, decreasing, and constant. Those are the first three. And when you're thinking about the properties or the characteristics of a function, you want to be reading the graph from left to right, just like we read left to right. So reading from left to right, and we're looking at the properties of the function through the x-axis. So we're always going to describe whether the function is increasing, decreasing, or constant through the x-axis. We always describe the properties of a function through the domain. Now, really important qualifier here. This says open intervals, and not all books are super clear on this. And so we want to be careful. When we say open interval, we mean an interval that does not include its endpoints. So an open interval is something like this, like 2 to 5. That's an open interval. It doesn't include the endpoints. And the reason our focus needs to be on open intervals is that when you get into calculus, you talk about two types of things: derivatives and integrals. And your analysis necessarily has to be with regard to an open interval. You will see in calculus that if you have a closed interval, things can be funny at the endpoints. So all the good calculus, they'll give you an open interval because it's really easy to generalize what happens on an open interval. But when you have endpoints, things can get a little fishy. And when you go beyond in calculus, so in Calc 3, instead of looking at intervals, you're looking at domains that are two-dimensional. So they're regions in the xy plane that are your domain instead of an interval on the x-axis. And when you get into that case, the boundary has an infinite number of points. And so it becomes virtually, I shouldn't say impossible to analyze what's happening at the boundary, but it's difficult. And so if you stick to open domains, it's a lot easier. And so we want to get into the habit now of just sort of thinking about open intervals as the part of the domain that we're going to analyze the properties of a function on. So open interval, parentheses, not brackets. So this says the open intervals on which f is increasing. So increasing means that if you move to the right on the x-axis, the y values are going up. Not the same, not down. They're going up. That's increasing. Pretty intuitive. And when we look at this interval here, we are saying to ourselves, all right, it's actually, let me get the highlighter for that. So right here is where the function's increasing. And again, we describe it through the x-axis. So we look down, that's x equals 1. And it says open interval, though. So we go 1, comma, and 4 is where it ends. So that is the open interval on which f is increasing. It is actually correct to say that it is increasing on that interval, but that's not what it's asking. It's saying find the open interval on which it's increasing. According to the definition of increasing, you could, this satisfies the definition. As you move through this interval left to right, the y values are going up. But if it asks for an open interval, that's what your answer should be. So just be careful on what's being asked. If it says on the open interval, it should have parentheses. Decreasing means the function's going down to the right, so that's certainly decreasing, as is this. So we'll have two intervals there. So we'll be decreasing. The x value here is -1. The x value there is 1, so -1 to 1. And it's also decreasing 4, and that's an arrowhead there, so it's going forever, so 4 to plus infinity. So those are the two intervals on which the function is decreasing. Two open intervals. And open interval where it's constant, pretty obvious. Let's see, stick with the same color here. Open interval where it's constant, so -infinity, this x value is -1. Bless you. But again, we don't put a bracket. If the question's asking for an open interval, leave parentheses. All right. Let's talk about relative maxes and relative mins. Oh, there's a link here to a pretty good Khan Academy video that has to do with characteristics of functions. It's a pretty decent one. So relative minimums, relative maximums, and did I put the definition up there? Let's just take a look at this definition. It's a very intuitive definition. A relative max is basically a y value that's above the surrounding y values. A relative min is a y value that's below the surrounding y values. So if we look at the formal definition, it says that f of c, so that's the y value at c, is a relative max if there exists an open interval I containing c such that f of c is greater than f of x for all x and I. So what that says, the breakdown of that, we're looking right there, intuitively say, oh yeah, there's a relative max there. So the relative max value is 2, and it's occurring at -8. And it's satisfying this definition. This is a really important subtlety here. So there's an open interval containing c. So when we look down here, there's an open interval containing -8, right? So that relative max is at -8. The relative max value is 2, but the relative max occurs at -8. So we have to distinguish between what the relative max value is and where the relative max occurs. So we're saying that the relative max occurs at -8, and the relative max value is 2. And so this, the way they define this, it excludes endpoints. Right? You see that it excludes endpoints? Because there has to be an open interval down there in the domain. So if we were dealing with a piecewise defined function that, let's just suppose it went up like that. So if we have this function that's just defined, and that's a really bad example. I need a curve. Let's get rid of that. I need something that does something more interesting. So let's suppose we have something like this. Let's suppose that's up at 5. Let's suppose that's at 1. Here we would not conclude that there's a relative maximum at 1. We would not conclude that because the definition says the function has to be defined on either side. That's what the definition says. It says the function has to be, there's an open interval I containing c. So that I has to be in the domain. And right here, we can't put this, there's no open interval here that we can choose because the function's not defined over here. So we have to have that open interval down in the domain for us to talk about whether a point's a relative max or relative min. So that we would not consider a relative max. All right, let's go back to this one. So let's look here. All right, let's get the obvious ones out of the way. Right there, clearly a relative min. That's the classic relative min. It's sitting at the bottom of a cup. So here we have a relative min value of 2, and it occurs at -1. So relative minimum, the relative minimum is 2 at x equals -1. So the minimum value is 2, and it's occurring at -1. And it's relative. When we say relative, that just means close by. It's the lowest point close by. Different from absolute minimum. An absolute minimum would look at the lowest function value overall. This one would have no absolute min because it goes down forever. But it would have an absolute maximum, right, because the function does not ever go above that point. So it would have a relative absolute maximum. Okay, other relative mins. Anything else? No. All right. If you have a question, make sure you ask, because it's a little subtle sometimes. Relative maximums. The obvious one is right there. So relative maximum value, it looks like that's 11. Relative maximum of 11 at x equals 4. All right, so let's get over here. Let me get some of this shading out of there now. That is a candidate. That's something that you're probably all looking at and you're analyzing, trying to decide, is that a relative maximum or not, right in there. So, is 6 a relative maximum? Yes or no? And the answer is no, because the function is not equal to 6 there. It's getting closer and closer and closer to 6 right there, but it's not equal to 6 there. So 6 is not a y value for the function in this neighborhood here, in this region. It's not a y value. So right here, there is no relative max. Okay? Now, what if we changed it a little bit? What if we put this as an open circle down here and we close that? How about there? Would 6 be a relative max there? So the definition says, is the function defined on an open interval below the 6, and is the 6 sitting above all the surrounding y values? And what would the answer be there? Would that be a relative maximum? Yes. Yes. There is an open interval around -1. The function's defined on that open interval, and in that open interval, that y value is greater than all of the surrounding y values. So in that case, it would be a relative max. Okay? So if it was included, it would be a relative max. Even though the function's not continuous here, the important thing is that the function is defined all through this interval here. All right, so, but for the original problem, we only have that. Let's go to the next one, do some more of this. And so here, let me just write the conclusion here. So this, we concluded that 5 is not a relative max here. And our issue is that we don't have an open interval that's in the domain of this function. That points at an endpoint. We don't consider endpoints where relative extrema exist. Now, if this question, let's just do one further bit of analysis here. If this question said, what is the absolute max? There you would say that the absolute max is 5. When we consider absolute maxes, we consider the entire function, not just the open part of the function. So if there was a question that said absolute max, you would first look on the inside for looking for all relative maxes, but then you would also consider the endpoints. So the 5 would be considered an absolute max, not a relative. Not a relative. So 5 would be an absolute max. Okay, so let's analyze this graph. Let's get this stuff off of there. All right, open intervals on which f is increasing. minus infinity to minus 8. Definitely. Open interval, so we put parentheses, no brackets. And then it's also increasing here, so negative 3 to negative 2. That look good? All right, open intervals on which f is decreasing. So again, we're reading left to right. Decreasing means it's going down, so negative 8 to negative 6. And that's it. That's the only interval where the function is actually dropping as you move left to right. Open interval where the function is constant, so negative 6 to negative 3. Relative mins. All right. Let's take a look right here. Is that a relative min? No. For it to be a relative min, it has to sit below the surrounding points, below its neighbors. And it's not sitting below its neighbors. Right? It's equal to its neighbors right there. So that value of negative 2 would not be considered a relative min, because it's got to be sitting right below. Another way to think about relative min is that if you're going from left to right, the function is going from decreasing to increasing. Now, relative max, it's going from increasing to decreasing. And you'll study that a lot in calculus, these points here where it's going from increasing to decreasing or decreasing to increasing. And just as a foreshadow, there's something called the tangent line. And these places where there's a relative max or a relative min, the tangent line will have a slope of 0. We're going to get into something called the difference quotient really soon. And the difference quotient is something that finds the slope of a curve. And the slope of a curve at a particular point is considered to be, by definition, the slope of the line that's tangent to the curve at that point. So you've always talked about slopes of lines. And when we talk about slopes of curves, the slope of a curve is simply the slope of the line that's tangent to the curve at that point. So when we have a relative max or relative min, the slope of that tangent line is 0. So that's how you will be able to identify relative maxes and relative mins pretty easily. Okay, so relative min, not there. Any relative mins? None. Relative maxes. So certainly we have a classic relative max there, max of 2. And that's occurring at x equals negative 8. Another candidate would be right there. But we conclude that it's not a relative max because it's not sitting above its neighbors. It's sitting above some of the neighbors, but then it's equal to the others. So not a relative max. All right, any questions on that? Yeah.
Part C for constant and like negative also would be constant.
Oh, I'm sorry. Yeah, absolutely. Forgot looking, I stopped reading from left to right. Absolutely. So we went negative 6 to negative 3 constant, and then also it picks up again as constant from negative 2 to positive infinity. Thank you. Yes, absolutely. Good catch. All right, so let's move on. Now, one thing, this problem looks a lot harder than it is. We have a triangle here, and it gives us some information about the rate at which the balloon is rising. It's rising at 120 feet per minute. Calculus is all about rates of change. That is the primary underlying concept that you're wrestling with throughout calculus, is rates of change. Calculating rates of change, analyzing rates of change. And that's what they're trying to convey here. As this balloon is moving up, the hypotenuse is changing, and if the balloon is moving up at a particular rate, that means the hypotenuse must be changing at a particular rate. And it's very common in calculus, to have to write a particular variable as dependent on another. And sometimes the choice is yours. You can choose, should I write y as a function of x, or should I write x as a function of y? Sometimes it depends. Sometimes one is better than the other based on the context. And here, d is simply this distance from the observer to the balloon, and we just want to write that as a function of t. And it's not hard, right? We have Pythagorean theorem, but that's the terminology. Getting this terminology down is really important. So d squared will equal 400 squared plus 120t quantity squared. So now we've written d squared as a function of t. So that right there, d squared is a function of t. And if we want to write d as a function of t, and you can include this of t, or you can leave it off. It's pretty obvious when you look at the right side of this equation that the independent variable is t. This is just a functional notation that sometimes it's really helpful to know what is the identified independent variable. Do you have to put it? No. Like right there, it's obvious that the independent variable is t, so you could put it or you could leave it off. It just depends on the context. But we've now written d as a function of t, and we can simplify that. I don't care about that right now. But the important thing is that conceptually, you're now thinking that d changes as t changes. T is independent, and as it's moving around, d is moving around. So we're writing d as a function of t there. All right, similar type of thing. We have a gas tank. It's got hemispheres on the ends that have each of the hemispheres has a radius of r feet. Cylindrical midsection is 6 feet long. Express the volume of the tank as a function of r. Okay, so the volume of this tank is a function of r. So we need to basically, if you think about splitting it into 3 regions, you've got 2 hemispheres and you've got 1 cylinder. You could take the 2 hemispheres and glue them together as a sphere. So you're basically trying to find the volume of a sphere plus the volume of a cylinder. And as you get into calculus, those are 2 shapes that you will see all the way through calculus. Spheres and cylinders are everywhere. So that is a good formula to eventually have remembered, 4/3 pi r cubed. Volume of a cylinder, you take the area of the base, multiply it by the height. Just like a rectangular box, you would find the area of the base, multiply it by the height. For a cylinder, find the area of the base, pi r squared for a circle, and then multiply it by its height. Will give you the volume. All right, so for us here, we have v as a function of r. And again, putting the independent variable like that, it's helpful in certain contexts, and others you may not need it. It just depends. You have to get comfortable with both. So we'll take the volume of the sphere, 4/3 pi r cubed, and that's our unknown. We don't know what r is. And then we have to add the cylindrical piece. That has the same radius, so that's going to be pi r squared. That's the base of the cylinder. And then we multiply that by 6, which I'll drop in front. So now we've written the volume as a function of r. And so one of the things you'll do in calculus is say, okay, well, what if the radius changes by 0.1 feet? How does that affect the change in volume? So a lot of analysis that you do in calculus has to do with optimization problems and manufacturing problems. If you're trying to build a part and the radius could possibly be off by 0.1 feet, how does that affect the volume? Does that keep the tolerance of your volume within spec or not? So coming up with your formula for volume as a function of one variable allows you to do calculus on it. You can do this thing called the derivative of it, and you can analyze how a change in R affects a change in V. All right, so another one. So another common type of problem in calculus. We've got some geometric object constrained by another geometric object. So here we have a rectangle constrained by a circle. So the rectangle is x feet wide, and it's inscribed in a circle that has a radius of 8. All right, we don't know the height of the rectangle or this triangle immediately, but we can calculate that. So we see the triangle, Pythagorean theorem is jumping out at us. And so we see that h squared will be equal to x squared plus 16 squared. So we can write the height of that rectangle as the positive square root of x squared plus 256. Take the positive square root because height is non-negative. So in the context of an application, you often decide whether you need the plus or the minus. In this case, we choose the plus. Okay, so now part A says express the area of the rectangle as a function of x. So for part A, the area as a function of x. So if we write area up here as hx, we've written the area as a function of two variables. We've written it as a function of both h and x. And that is a hard thing to analyze when you have two independent variables. In Calc 1, you really want one independent variable so you can do these things to it, like taking derivatives and setting them to 0. So for the area, to force it to be a function of one variable so we can do calculus on it, we rewrite the height as a function of x, and we can then use that to find the area here. So the area is going to be x times, we're basically just substituting, right? So that would be the area of the rectangle as a function of x. And so one of the common types of problems that you'd want to be able to do is to figure out what the maximum possible area is. And so what should the dimensions of this rectangle be to make it the maximum possible area for that rectangle that's constrained by that circle? And so when you get to calculus, you'll take the derivative of this, you'll set it to 0, and you'll figure out some things. Okay. But for us, we're just analyzing the function in a general sense. It says, for part B, find the domain of that function. So domain, you could say the domain of this, there's two different types of domains. There's the implied domain, and there's the explicit domain. All right, so an implied domain is just the set of all x's for which it's defined. So when you look at that, is there any x that you could plug in here that causes it to be undefined? No, right? X squared is inside the square root, so the inside's never negative. So you're never going to take the square root of a negative. So that implied domain is all reals. But that doesn't fit with the context of an application. So in an application, you generally are going to go with an explicit domain. You're going to say, I'm only considering the x's that are greater than 0 and less than 16 or something. So we have to analyze for this particular problem. We're dealing with a rectangle. X can't be 0, then we don't have a rectangle. So x has got to be bigger than 0 to make sense of this. And then we also have to deal with the height being bigger than 0. So we've got to sort of think about what our extreme options are. Okay, so we're going to choose our domain of A to be the set of x such that x is going to be certainly greater than 0. Then we have to figure out what it has to be less than. Well, what happens, what do you think? We know the diameter is 16. So if the diameter is 16, if we imagine, so we said x has to be bigger than 0, but as we squash this rectangle, isn't 16 the other limit? Right? We could never have x being greater than 16 is the diameter. So if we get to 16, then we've collapsed the rectangle into a line segment. So we want that x to be greater than 0, but it also has to be less than the diameter. So it's got to be less than 16. So that's going to be our explicit domain. That's going to be the domain that applies to this particular application. X is outside of that, don't give you a rectangle. Then it kind of defeats the purpose. All right, graph the function with a graphing calculator. So we can graph that in Desmos easily. What dimensions maximize the area? So we can do that using a calculator. In calculus, you would do the derivative, and you'd set it to 0, and you would find it. For us, all we can do right now is graph it and take a look and see, hey, what is the x value that makes the area the biggest? So let's just go over to Desmos and graph that thing. And so x and then square root, I'll do x squared arrow plus 256. And to get a square root symbol, I'll go up and just do 0.5. All right. And brighter. Let's go out. All right. So we only really care about 0 to 16, right? So here's a couple of things I could do. I don't see the graph up there. I'm going to label this. I'm going to say that this, I'm going to use functional notation to call it that. And then I want to see where the point is when I plug in. I'm going to make a point. Capital P will make a point. And let's do 16, comma, f of 16. Whoops, I didn't do f of 16. Parentheses, 16. That should now put a point on the graph. Hopefully it did. I did put a comma there, right? All right, so let's go look. So when we get up here, well, I guess we could just do this too. All right, so there it is. So that, I'm a little surprised that that's our. Do we have the right area function? I thought we were, I was expecting us to see
h squared plus x squared equals.
Say that again?
The function was not correct.
Oh, that function's, oh, it's 20, oh.
It should have been h squared.
Yeah. I know exactly what you're saying. Yeah, that's not right. Is it? It's the diameter squared, right? Hypotenuse squared. Right? Pythagorean theorem? I did the Pythagorean theorem wrong. I had the plus and the equals in the wrong place. That is the Pythagorean theorem, right? Leg squared plus leg squared equals diameter squared, or the hypotenuse squared. Yeah, something looked very fishy over there on that graph. That did not make sense. The area could not have been maximized when the x is 16. When x is 16, we can see here that we're going to get a line segment. We're going to have no area. All right, so it should be 256 minus x squared. And so this should be 256 minus x squared in there. Yeah, that's better. Now we will see area being maximized. All right. Very suspicious. Minus x squared. That is more like what we would expect. Okay, so let's see, so 16. I'm not seeing my point now, though. Where's my blue point? It should be on the x-axis. Oh, there it is. It should be on the x-axis. All right. That's what I expected to see originally. Didn't. What is that? All right, so there is our max right there. And in Desmos, you actually can touch anywhere near it, and it's going to grab it for you. It's going to automatically pick that highest point. So this tells us that's the maximum area, 128. So 128 is the max area, and it occurs when x is 11.314. Right? But we have no other way to find that right now except with technology. If that was a parabola, you know how to find the high point on a parabola, but it's not a parabola. That thing is not a parabola. That's x times the square root, so not a parabola. So max value of 128. So actually, we might as well capture that graph and just put it, where's my camera? Let's just grab a piece of that graph and put it in here. So, all right, and then the last part of the question is asking us for the dimensions. What dimensions maximize the area of the rectangle? Oh, okay. Well, we just said the x value has to be 11.314. Then if the x is 11.314, we would plug that in here to figure out the height, to get the dimensions of that rectangle. So we're approximating. There's part C, part D. X equals, let's just go to 3 decimal places since that's what it did. And then the height, we would plug it into that function. Oh, I didn't bring my calculator. So somebody type in 256 minus 11.314 squared and take the square root. Tell me what you get. Oh, 15.6?
Square root, right?
Yes, square root of 256 minus 11.314 squared.
11.31.
That's what I would expect.
That's what I got.
Yeah. Bless you. That's what I expect. And if you think about it conceptually, if you're trying to maximize the area for a rectangle, 9 times out of 10, it depends on some other constraints, but when you're constrained by just a circle, a square is going to be the biggest area. Yeah. So whatever units are, did they give us units in this one? Feet. So, yeah. So that's a common sort of conceptual thing that you'll start to see in calculus. That, oh, maximum areas are often super, nice polygons, like a square. All right. The piece of Math 121, College Algebra, that there's a lot of struggling with is our piecewise defined functions. And they're super important. Super important to be able to understand them. So let's just spend a little time graphing piecewise defined functions. Piecewise defined functions are defined differently for different pieces of the domain. So when you're looking at one of these functions, you're thinking of the qualifier on the x over here. That's the piece of the domain. So this says when you're in the part of the domain where x is less than or equal to -2, that's your y value. When you're in the piece of the domain where x is greater than -2, that's your y value. All right, so you've got to pick which y value do I choose. Well, it depends on which piece of the domain you're in. And the function that you've all dealt with, that's a piecewise defined function, you've dealt with it for a while, is the absolute value function. The absolute value function is a piecewise defined function. It's either equal to x or negative x, depending on what piece of the domain you're in. Absolute value of x is exactly x if x is greater than or equal to 0. And it's minus x if x is less than 0. Does that make sense, that definition? You all know what the graph looks like, and you all know absolute value of -5 is 5. Like, that part's easy. Do you look at that, and does that make perfect sense? So what we're doing here is coming up with a formula for the y values. So we have to come up with a formula for the y values based on the x value. So if x is greater than or equal to 0, the y value is found by just erasing the absolute value bars. Okay, so if it's greater than or equal to 0, it's itself. But if x is negative, to get that positive answer, we multiply it by -1. So if in here you have a -5, this is telling us that the y value is -5, which is +5. So it's giving us a formula to get the correct y value. Okay, so let's take a look at this piecewise defined function. We're going to start with the top piece. So for x less than or equal to negative 2, the y value is 3. So when we look at the graph of this, less than or equal to negative 2, the y value is 3. So right there, and then we're going straight left like that, constant. That part makes sense for that piece? So the y value is exactly 3 for all the x's that are less than or equal to negative 2. Now, to the right of negative 2, this is the y value. So if we plug in negative 2, even though it says greater than or equal to, even though it says greater than, not greater than or equal to, we still plug that negative 2 in to see where it wants to be, to see where it's approaching. So if we plug negative 2 in here, negative 2 divided by 2 is negative 1 plus 6 is 5. So it wants to be at 5. 4, 5, negative 2, 5. So we put an open circle there. What's the y-intercept for that piece? 6. And so there is the rest of the graph. So it's linear, so it's a line, but it's only part of the line. It's a half line. Okay, let's make sure this is clear. What is the domain of this function? And what is the range of this function? Domain of f? All real numbers? Does everyone agree with that? It's all reals because there's no x value that's missing. For any x value that you pick, there's going to be a corresponding point on the graph. If you pick negative 2, there's the corresponding point. If you pick over here, there's your corresponding point. So every x has a corresponding point. So there's no x's left out, so the domain is all the set of all reals, which you can write like that, or if you want to write it like this, you can do that also. Either way. How about the range of this function? Is 4 in the range? So it's not 3 to infinity. That's your first instinct because you sort of see that it starts at 3. But there's a gap, right? There's a gap. These y values greater than 3 and less than or equal to 5 are not in the range. Right? There's no points on the graph that correspond to those y values. So when we write the range here, we have to write it as a singleton point of 3 union, let's see, doesn't include 5, so it's going to be a left parenthesis, and then it's going up to positive infinity. So that'll be the range. All right, number 50. You guys graph number 50. Number 50. Oh, I didn't finish. Let me finish 48, actually. Sorry, let me finish this first, then we'll do 50. So it says, what are these 4 function values? F of negative 5. We look, negative 5 puts us in this piece, so the y value is 3. F of negative 2, that puts us in this piece also. Less than or equal to negative 2, the y value is 3. F of 0 puts us in this piece. 0 is greater than negative 2, so you plug in a 0. 0 plus 6, so you get 6. And then f of 2 is also in that piece. Plug it in right here. 2 divided by 2 is 1. 1 plus 6 is 7. All right, now do 50. 50. Raise your hand if you're sort of stuck on any piece of it. No pun intended. And of course, for a line, you know that you need 2 points, so the end points are always good if you have a linear piece.
So it's negative, right? It's greater than both of them less than so this is also one positive to negative side. So you plug in your 4, like you did, you get 2, but then you have to plug in the second one.
Because you actually want to plug it in, even though it's not your, that's just kind of the start. And then you just have to figure out if it's going down or constant.
It was relative, but this first piece,
So when you look up there, the first piece, if you plug in -2, you see it right there. So for this piece, you're going to plug in -2.
So just concentrate on this one. So for everything less than -2.
That's still
So
-2, so that's going to give you 1
you're going to
point.
put
That's a lot.
-2 just to see
It's going to give you 1 point, and then you want to
Yeah,
put the
so
second
you
point.
have
That's
to
going to
open
be
it.
else.
And then you just need
Left
another
and -2.
another point.
So -2 and -3 would be your x's here.
Yeah.
The middle piece, those would be your x's. The third piece, that is one of the
same
x's.
thing. Jump over here, and this one's
Then you pick something
so,
else.
but you're going to do the same with
5.
five.
That would be your second point for that third piece.
I would do your endpoint. So then you know you only need 2 points.
So this
a
piece
lot.
right here,
Right. So you might as well see what your endpoints are doing.
you're
Especially
showing
because they're
constant.
included, so you want to.
So we do it for that piece, is that first piece constant?
To start where you're not supposed to be, but that's
Negative
really
5x
where you want
minus
to
8?
Start.
That's a lot. So if you plug in your first point correctly, if you plug in -2, you're here. Right?
Yeah.
That 2 is 10 to the 2. Oh, yeah. Should be 2. This one? Oh, I was looking at the wrong one. Oh, you haven't started. Okay. So plug in -2. Each one of these is a line. Here you're going to plug in -2 and -3. Yep. Then, well, you have to, because it's a line, you do 2 points. So if you plug in -2, then you have to plug in 1 more point. Plug in something to the left of -2 or something. This line, plug in less than this. This line, plug in less than this. And then something to the right.
Just look at the very first one. Just start with -2, even though it's not included. Figure out that and then just take another point to be less than yeah.
All right, so let's start.
I was waiting.
Each one of the pieces here is linear. And so the key with any line is that you need 2 points on the line. And sometimes it's a stopping point. When you see that it doesn't include the -2, you don't want to plug it in. But you can plug it in. You just have to remember that if it doesn't include the equal to, then you have a graph with an open circle. So that's a great way to figure out exactly where that dot is supposed to be, whether it's an open dot or a closed dot. So for this line, x less than -2, plug in -2, get an open dot, and then plug in something to the left of -2, like -3. For the middle piece, certainly the endpoints are perfect. Most of you had that one, no problem. And then for the third piece, it's also a line with negative slope. Plug in 4, get an open dot, and then plug in 5, and that will give you 2 points for the line. All right, so at -2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so at -2, we're going to be at 2, but it's open, so I would do that. And then at -3, we have 15 minus 8, which is 7. So at -3, we're over here, all the way up at 7, so something like that. And then we're going to have a ray that's going off that direction. And it should be touching that open circle. I like that. All right, so that's the first piece. And then the middle piece, we can plug in -2 here, and we get -1 plus 5, so it's going to be -2 comma 4. About there. Whoops. -2 comma 4. And then we plug in the 4, and we get 7. So we're coming out here to 4, and we're going to get 7, which is right there. And this, for this line segment, we're including both endpoints. Let's see. And that looks pretty accurate. The y-intercept also lines up. If you plug in x equals 0, you should be at 5. So that's pretty good. Oh, no, it's not. 1, 2, 3, 4, 5. That's not lining up very well. Oh, because I have that point too high. That point's not at 4. 1, 2, 3, 4. It should have been down here at 4, right? Yeah, it should be more like that. 1, 2, 3, 4, 5. Now it's lining up better. All right, then we jump to the right. Plug in x equals 4. 10 minus 8 is 2, and that's going to be an open circle. Right there. Pick something to the right of 4. Simplest thing is to plug in 5. Plug in 5, and what do we get? 0. So that's going to be our y-intercept, and that is going to give us the third piece right there. And that's an open circle. All right, so there's the graph of that function. What is the domain of this function? All real numbers. Does anyone disagree? Are there any x's that are missing? The only candidates for possible missing x's would be somewhere in this region and somewhere here where it's broken up. But no, there's each of those transition points has a y value. So all reals, definitely all reals. Okay, now the range. So the range, we start at the bottom of the y-axis. So starting down here at -infinity, and we start working our way up. This arrow going straight down means we have y values all the way up, all the way up to there for sure. And what happens at 2? Is 2 a y value for this function? No. Right? Both the 2 spots have open circles, so y equals 2 is excluded. Then let's go above 2. Is there any other y value that's not corresponding to a point on the graph? No. So the range starts at negative infinity, goes up to positive 2, doesn't include it, but then it picks up again right away. So the range would look like that. We have to pull out one number.
Why
Yeah.
are there brackets around the infinity?
So infinity is not a number, so it can never be included. So we never will see infinity with a bracket on it. A bracket means include. Infinity is not a number, it's indicating a concept. The concept here is that we're going 2 to the right forever. So you're never going to see a bracket on infinity because it's not actually an endpoint. Right? It's giving us just a road map. It's saying all the x is greater than 2. So we'll never see a bracket on infinity. All right, why don't we take a break there, and then we'll do a couple more of these when we get back in. Piecewise functions. All right, let's do these last 2 piecewise ones. See if you can do number 54. 54 should be actually a little easier than the last one because there's only 2 pieces. So try that. Once you get it down, I think you'll be fine with it. It's just, it can be a little challenging when you're looking at those pieces. But once you understand all the moving parts, it's just a matter of, finding your transition points and your closed dots and your open dots. It's amazing how much of math is notation. Being able to decipher the notation. Graphing dots, good thing. Graph those dots. So in some ways these are easier because all the pieces are linear. Certainly we're going to have some examples in the homework where the pieces aren't all linear. You could have a quadratic or something. But with these linear ones, you really get in the habit of graphing 2 points, including the transition points, and you're good to go. So in this first one here, 2 is the point I would consider a transition point. And the top piece is for numbers that are less than 2. We still plug in the 2, though, and we get 3. So 2 comma 3, and we put an open circle. And then a second point on that linear piece, we'll plug in -3, or -3. we'll plug in anything to the left of 2. Negative 3 would work, but the more natural thing to plug in would be 1 or 0. And if we plug in 0, we get negative 1. So that's right there. And so that's our first piece. And just remember, open circle on the 2. For the second piece, 2 also. And we get 0 there, and we include it, so we put a closed circle. And then a couple of choices. You could look at it and say, hey, the slope is -1. And so you could go down 1 over 1. That would work. Or if you want to keep it super simple, just pick another point. Plug in the one next door. 3. 2 minus 3 is -1. And you get that point. And so there is our second piece. So that's the graph of our function. The domain of this function, all reals. How about the range? Starts at negative infinity. And then where does it end? 3. And do we include or exclude 3? And we exclude it because there's an open circle there, not a closed circle. So we put a parenthesis, not a bracket. Question? All right, so this last one here, we have that x is constant, x is 4, y is constant, when x is less than or equal to -2. So for that one, here we do get this constant ray. So -2, 4. That should look like that. And we're including the point at -2, 4. So that's the first piece up there. Second piece is a line. So we'll plug in the -2, plug in the 3, and exclude the endpoints. So plugging in -2, -2 plus 1 is -1. And we put an open circle. And then for the other transition point, 1, 2, 3, plug in 3, we're up at 4. 1, 2, 3, 4, and we put an open circle. So that would be the middle piece. Any questions on that? So again, if you have a linear piece, plug in an endpoint. And if you have 2 endpoints, plug in them both. And then the third piece, for x greater than or equal to 3. So if we plug in 3, we get -3. And that should be included, so closed circle. And now again, that's a line with slope -1. So you could do that, right 1 and down 1 if you want. Or just plug in another point. The neighboring integer point would be 4, so 4, -4. And that'll be a half line, a ray, down to the right. All right, domain and range. What's the domain of this thing? Yeah, all reals. There's no gaps, vertical gaps, right? No vertical gaps. Range. There's definitely a horizontal gap, though. So the range, we start way down at negative infinity. We work our way up the y-axis. And then we stop at -3. And then there's a gap. So -3, and then we include the -3 this time, because it's a closed circle at the -3. Then there's a gap, and it picks up again at -1 with a parenthesis. Exclude -1. And then what? 4 with a bracket, exactly. That's where it ends. 4 with a bracket. Good. So range coming from the y-axis, domain coming from the x-axis. Everybody okay with that range? So you're coming up the y-axis. You're seeing why we have the gap and why we end at 4. Cool. All right, let's do one harder one. So The top piece, the first piece, is a rational function. And you should remember from college algebra that rational functions have asymptotes and possible holes and all sorts of crazy things. The thing that I like to do with rational functions is factor if possible. And do you see that the numerator factors into that? So, what happens at -1?
Point at 7.
Say again?
There's a point at 7.
At -1, there is going to be a point at 7. What happens to this at -1? Whole. Whole?
Yeah.
So, if you have a rational function, the zeros of the denominator are vertical asymptotes unless there is a common factor with the numerator. If there is a common factor with the numerator, there is then a whole. Okay, so here, this tells us that we are going to have a whole at x equals -1, not a vertical asymptote. So if there was an x plus 1 in the denominator and not an x plus 1 in the numerator, then we would have a vertical asymptote at -1. Right? So that's a whole. And what would the y value of the whole be? So don't look here, just look over here. What would the y value of the whole be? Anyone know? What if you canceled those out? Yeah. The y value of the whole is found by substituting the x value into what's left after you cancel out the whole. So the y value would be -1 plus 2. We're plugging it in to that, and so the whole is there. All right, let's finish this one off, and then let's do. I see a couple of blank looks. So let's do a little bit of review of rational functions after we finish this one off. All right, so for graphing this one, the graph of this piece is the line x plus 2 with 1 point removed. So we get a punctured line. So the y-intercept is 2. Let's see. And the whole is at -1, 1. And slope is +1. So that point should be on it also. So let's move you up just a smidge, and this will be our graph. So we've got this punctured line, line minus 1 point. Cha. All right, so there we go. That's our graph of the first piece. All right, now the second piece is obvious. It's just a singleton point. So -1, 7. So I'm just going to put it up right there. It's -1, 7. So there's our graph. The domain, all reals, no vertical gaps anywhere. No, every vertical line meets the graph. How about the range? Yep. And then, yeah, exactly. So we have we just have to take out 1 point. So we take out the y value of 1. That's the only y value that's not attained. Every other y value is attained. This one is attained twice, 7. Doesn't matter, though. 7's part of the range. It's okay if it shows up more than once. Okay, let's do a little bit of rational function review. So let's just start with the simple function. I want to just compare the following function. So the following functions. So the graph of y equals x, right? That's a line. Just like that. If, for whatever reason, you want to take one point off that graph, here's what you do. If I want to take a point out at, say, -2, I do that. The graph of this is going to look really, really similar. Can I just grab the graph part of it? It's going to look really similar. And so it's going to be that, except we're going to be missing one point. So at -2, -2, we need to take out a single point from the graph. So we have to remove one point. So let's see if we can. Let's see, that's not what I want to be doing. What the heck am I doing here? I'm trying to change the color here. So if I grab that, I should be able to change the color to white. And then we can take out that one point. All right, so we take out that one point. So we have a hole in the graph now right at that one spot. So that's what the graph looks like. So you can take points out by multiplying top and bottom by a common factor. When you're asked for the domain of a function, you have to look at the presentation of the function in its original form. This certainly reduces to x, but it reduces to x with the caveat that x is not allowed to be -2, because that's how it was presented originally. So it's true that it reduces to x, but we have to abide by the original restriction that x is not allowed to be -2. So the domain of this function is all reals except for x being -2. So and we can do this with other types of functions also. So let's suppose we have f of x equals x squared, and let's multiply by x plus 3 over x plus 3. That's going to be the graph of x squared with the point at x equals -3 taken away. So the graph of this is going to look a lot like x squared, almost exactly like x squared, except one thing is going to be missing. We are going to take out one point at -3, 9. There's one point missing. Can I glue that back together? Oh, no, it's still all attached. So it's a big hole. But that's just one point removed at -3, 9. So this will have a hole at -3, 9. We get the 9. If we cancel these common factors, we plug the x value of the hole right there to get the y value. And so again, if the numerator doesn't have a common factor, you get an asymptote. But if it does, you get a hole. Let's see, let's go back to here and finish these guys off. Determine the domain and range, and then write an equation for the function. Okay, here goes. Domain and range is easy. We're getting good at that. This first one, we definitely see that the domain is all reals. All right, range is always trickier. So range, what's the first part of the range? Yeah, -2 all by itself. So a singleton set, a set with just a single number. union Yep, so we're coming up, and boom, we get one single point in the range, one y value that's used right there. And then we come up, there's that gap, and then we start at 0, and then that goes up for infinity, up to infinity. Okay, so union bracket 0 plus infinity, parenthesis, because we never put a bracket on infinity. Okay, now we have to come up with an equation for that thing. Zoinks. Okay, so f of x, how many pieces should we have? 3 pieces. So let's start with the left one. That's a line, and you can clearly see 2 points on it. And you notice that it's actually bisecting quadrant 2. So what is that line that bisects quadrant 2? Negative x. Y equals negative x. So this is negative x if x is less than or equal to 0. We're including the origin, so we can put less than or equal to there. Great. Now we go to the middle piece, and that's very similar. It's y equals x if x, let's see, so we included 0 there, so we won't include it here. And that goes over to 3, and we exclude 3 because there's an open circle. And then the last piece, the third piece, the y values here are negative 2 if x is greater than or equal to 3. Good. Let's try. Let's see, you guys try this one. See if you can. Domain, range, and then equation. 3-piece function. John Paul had an interesting point on this previous one. We included the 0 with this first piece and excluded it with the second piece. You could change that, and it would be totally fine. You could include it with the second piece, exclude it from the first piece, but you wouldn't want to include it in both pieces. Because you're breaking apart the domain into distinct subintervals. There's no overlap between them. So one or the other. So everyone see that we have 3 linear pieces here? And this first piece, if you look at your x interval, it's going to go -4 to -1. And here it's similar to the previous one. You can either include the -1 with the first piece or the middle piece. Doesn't matter. I'll include it with the first piece. So then my second piece is going to go from 1 to 2, excluding the 1 and the 2. And the third piece is going to be greater than or equal to +2. Say that again?
Should that be -1?
This should be -1, yes. Yeah, thank you. Yeah, -1 to +2. All right, so that first piece, line, we need to find the equation of a line. So we need 2 things to find the equation of a line: slope and a point on the line. Everybody agree with that? Slope and a point. If you knew your y-intercept, that would also work. And this is pretty nicely, we can see the slope is -2. So we could write this one using slope-intercept form or point-slope form. It's not going to matter. Let's do it with point-slope form because that's the more general approach. It's kind of uncommon that you just happen to know the y-intercept. So point-slope, for that first one, we know that the slope is -2, and that point up there is -4, 4. And then the equation, we do y minus y equals slope times x minus x. So it would be -2x minus 8, but then we're adding 4, so minus 4. And that lines up with where we see that the y-intercept would be. So -2x minus 4. Usually I put in if. Does that look good? Remember how to find the equation of the line? So point and slope. The middle piece, let's go through that. Same idea. Am I green? I'm green. I'm not white. Okay, so the slope here is +1. And a point, let's pick -1, -2. So again, it's y minus y equals slope times x minus x. So we end up with x plus 1, subtract 2, so y equals x minus 1. And that matches the y-intercept that we see. We see a y-intercept of -1, and we see a slope of +1, so that matches. So that's our middle piece. And then the easy one, our last piece, it's 2. A constant 2 if x is greater than or equal to 2. Good? Makes sense? All right. So, that looks like a mess. Graphing piecewise defined functions. This is just an example of how you can graph a piecewise defined function using Desmos. So this is just, if you're playing around in Desmos and you want to graph a piecewise function for some reason, there's multiple ways you can do it. So let's first just take a look at the blue one. So the blue is just a line that is going to stop, I should say a ray. It's a ray that starts here and it goes on forever to the right. So in Desmos, I graphed y equals x minus 2, and then in brackets you put your piece, you put your restriction. So this is going to graph y equals x minus 2 only for x's that are greater than -2. Now it doesn't throw in an open circle unless you manually do it. But this is going from -2 on. To graph an open circle, that's down here. So if I just plot that point, -1, 2, then I can choose a property. If you click on the gear, you can change the property of something to be a solid dot or an open dot. If you want to modify the property. So if I wanted an open circle there, I could do that. All right, now let's look at the green one. So the green one, we have a trig function, we have a sine function here, and then we have y equals x. So this is another way to do a piecewise defined function. So I'm saying that if you put it all in brackets, for x less than 0, you're going to graph sine x, y equals sine x. Otherwise, you're going to graph y equals x. That's what that says. So it's going to be y equals sine x when x is less than 0. So sine x when x is less than 0, comma, otherwise, the rest of the line is graphed, the rest of the x's are graphed using this function. Okay, so that's a second way to do a piecewise defined function. We could have done this with two pieces separate. We could have done y equals sine x with this restriction x less than 0, and then a second line y equals x, x greater than 0. Could have done that. And then here's the third way. So third way is the purple function right here. This says when x is less than 1, colon, graph y equals 3. So when x is less than 1, graph y equals 3, comma, when x is greater than 0, graph 4. So that's the other piece. And then the orange one, I just added, that vertical thing is not supposed to be in there. That's just a, whatever they call it, artifact. It's not part of the graph, part of the input. So here, if x is less than 5, we're graphing -2. If x is between -4 and -2, we're graphing -3. If x is greater than 3, we're graphing x minus 5. So if you're graphing piecewise functions, it's a lot easier in Desmos than on graphing calculator. If you have a graphing calculator, trying to graph a piecewise defined function is just a lot of, you can do it. It's just a little bit time consuming. Okay. I think I just jumped 2 slides. Jump 3. All right, let's go here. All right, 2.2. So 2.2 is the only thing in 2.2 that we are concerning ourselves with is difference quotients. And again, I mentioned at the beginning of class, difference quotients are slope finders. In the numerator, you have change in y. F of x plus h and f of x are y values. You're taking the difference. H is a change in the x coordinates. So that is actually just a fancy way to write slope. So if we looked at a picture, just so it's clear what is where, if we have some curve like that, the idea is that we have our x plus h, and then on the y-axis, those points are corresponding to f of x plus h and f of x. So f of x plus h minus f of x is figuring out a difference in y values. And then h is the difference in x values right there. Right? So what that's finding is the slope of the line through those 2 points. That's generally referred to as a secant line. Does everybody see that? Change in y over change in x. That's all that is slope. And in calculus, the one thing that you're going to do is let this h slowly approach 0. And if you let that h approach 0, then this secant line starts rotating and it terminates in the tangent position. So for us, we're going to just keep it as a secant line. But next semester, you'll let h go to 0 and that secant line rotates into a tangent line. All right, so let's go ahead and evaluate some difference quotients. So the difference quotient for this function, we have to figure out what f of x plus h is. So we replace the x with x plus h. So that's this first part, f of x plus h. F of x plus h is f with the x turned into x plus h minus f of x. So this is f of x right there. So we have to subtract off f of x and divide it by h. All right, so distribute the 5. So this is going to be equal to 5x plus 5h plus 3 minus 5x minus 3. We're going to simplify. 5x minus 5x is 0. 3 minus 3 is 0. We're left with 5h over h, which reduces to 5. So the difference quotient reduces to 5. What is the slope of that line?
0.
Slope of this what about this line up here? 5x plus 3. 5. And we got 5. The difference quotient is a slope predictor, and a line has constant slope. So this is telling us that the slope of that function is always 5, which means it's necessarily a line of slope 5. So a line is the simplest object, of course. So whenever we do a difference quotient for a line, we always get the slope. All right, let's try a harder one. So -1 over x. So we plug that in up there. F of x plus h, we're going to have -1 over x plus h minus f of x. So that's the numerator. Does everybody see that that's f of x plus h minus f of x in the numerator? So f of x plus h minus f of x. So now we have to simplify that. To simplify this, we're going to multiply top and bottom by the common denominator. And that will simplify it. So we distribute this quantity to the first fraction over here. We send it across the first fraction. The x plus h's cancel, and we're left with minus x. We send it to the second fraction. We're going to get a plus, the minus and minus. 1 over x times x plus h. Now the x's are canceling, and we're left with an x plus h. And then in the denominator, we have h times x plus h. And that reduces to h over x times x plus h. Whoops. I forgot my h. And then the h's cancel, and we're left with this. All right, so there is the difference quotient for the function -1 over x. So that tells us the slope of the secant line. And if you plug in h equals 0, you get the slope of the tangent line. That's what that's telling us. Any questions on the simplification there?
Actually, yeah. How did you get to straight x? Or
Here?
straight h?
That right there?
No. On the next step.
Here?
Yeah.
Negative x plus x.
Oh.
So those two are just canceling out right there. Those are just adding up to 0.
I didn't see the plus between the x's and h.
No problem. Did everybody see that? Definitely ask. Always better to ask. Okay, let's, for each function, construct and simplify the difference quotient. right, so let's just do this one. This will be our last one in this with the difference quotients. So it's just a lot of algebra. We have to plug in the x plus h. We have to square it out. Go. Let's do it. Okay, so f of x plus h. I'm plugging in x plus h for each x in the function. So that is f of x plus h, right there. And then we subtract off f of x. And we have to make sure that we put that in parentheses. And then we divide by h. So now we got to FOIL this all out. We get 5x squared plus 10hx plus 5h squared plus 4x plus 4h minus 5x squared minus 4x over h. What you are going to notice every single time, you better get cancellation with each piece of f of x. It's always going to be true that those are going to cancel out. And do you see that h is common to all the terms left? So we can cancel out an h there, one of those h's, that h, and that h. We have to distribute it, so we're left with 10x plus 5h plus 4. So that expression is the slope of the secant line. And if we plug in h equals 0, we'll get the slope of the tangent line. The slope of the tangent line is what they call, in calculus, the derivative of a function. Right? Slope is the rate of change. That's what calculus is all about, rate of change. Notice some patterns here. This linear term, we saw earlier that the difference quotient for a linear function is just the slope, and that's what we get down here. Anyone care to venture a guess? 5x squared to 10x. What did we do there? There's a nice little shortcut. How do you get 10 from the 2 and the 5? Multiply. Multiply and subtract 1 from the exponent. That's going to be a calc trick that you're going to see. If you have something like 8x cubed, the derivative will be 24x squared. You'll just multiply and drop the power by 1. And that's what happens with the 4x also, right? This is 4x to the 1. Multiply 4 by 1 and you get 1. And then you subtract 1 from the exponent and you get x to the 0. X to the 0 is 1, so you get 4. So that always will happen. All right. Enough difference quotients. Transformations. You guys are great at these. You just did transformations with trig functions. Transformations with algebraic functions is going to be a piece of cake. Way less going on. Way less going on. So in this book, different algebra books have a different sort of handbook of basic functions. And in this book, they talk about these as the basic functions, basic 7 functions. Linear function, quadratic function, root function, cubic function, cubed root, the reciprocal function, and the absolute value. Some other books will include a couple of others. Doesn't matter. These are the basic ones that we're going to see in this book. And then we're going to do what we did with our trig functions. Shift them, reflect them, stretch them, or compress them. So we're going to do those same types of things. This is a list of all the transformations. We'll just go over it briefly, then we'll just do some examples. So we always are going to separate into vertical transformations and horizontal transformations. So if we focus for a minute on vertical, vertical shifts are on the outside. A vertical stretch or a vertical compression is a number that's on the outside, a multiplier. And then a vertical reflection is if there's a minus on the outside. So the way I like to break it down is I think of all the verticals as outside of the function. Just like in trig, it's all the stuff on the outside. Horizontal is all inside the parentheses. It's inside the function. And so with inside stuff, we have the same thing. We have horizontal shifting, which is opposite of what you see. So that's why they have that flipped upside down. And then with reflections, a reflection that's inside is going to be, instead of through the x-axis like a vertical reflection, it's going to be sideways through the y-axis, a horizontal reflection. In trig, it was cool because we could eliminate those horizontal reflections. We used the fact that trig functions are either odd or even, and we could get rid of the horizontal reflection. And with the algebra stuff, we can't do that. Sometimes you can, but not usually. And then, of course, horizontal compression or stretching. If you look inside and there's a constant inside, and what we notice is that it's opposite here. Outside the function, bigger than 1 means stretching. Inside the function, bigger than 1 means shrinking. Okay, so outside bigger than 1 is stretching. Inside bigger than 1 is compressing. And that makes sense conceptually, because a vertical stretch is the same thing as a horizontal compression. Vertical stretch, horizontal compression are the same. Okay, so we'll do a couple of examples where we can really see that. So that just kind of summarizes it. So we're going to call those 7 basic functions, and let's take a look at how we get the graph of these transformed functions from our basics. What's the basic function for g? Yep, root x. That's our basic function. And when we look at that transformation, g, nothing is going on outside. So there's no vertical transformations. The only activity is inside the root. So those are anything that's happening in the root is going to be horizontal. And what's that? A shift? What way? Shift right of 1. Okay, so then we go to our graph. Pretty straightforward. As long as you know, make sure you know your basic functions. If you know your basic functions, you're pretty good to go. So here is root x. And then g is going to be that function shifted to the right 1 unit. So that will be y equals g of x. Shift right 1. Next one. Basic function. Reciprocal function. So that's our basic function there. And then we have to do what? Shift. Is that -2 inside the function or outside of the basic function?
Inside.
That's inside. If it was a shift on the outside, it would look like that. If it was outside, bless you, outside the function. Okay, so this is going to be a shift, and horizontal shifts are always opposite of what we see. So that's going to be shift right 2. So we go to our graph. And 1 over x is the reciprocal function. It looks like this. It's a hyperbola. And recall that there are asymptotes for this hyperbola. Technically, it's a rotated hyperbola. And then we have to shift it. So we're going to shift it to the right 2 units. So that means that if we're shifting to the right 2 units, that means that our asymptote is coming with us 2 units to the right. So 2 units to the right, we've got to move our vertical asymptote. The horizontal shift does nothing to the horizontal asymptote. horizontal shift won't move that. But it will move a vertical asymptote. And so our transformation has a graph that looks like this in blue. So it shifts it to the right too. Okay, number 12. Our basic function here is absolute x. And then here we have multiple transformations. They're both vertical, though. They're both on the outside. So there's no horizontal ones, but we do have two vertical ones. So we have a reflection and a shift. And we need to know an order that always works. And the order that this book uses, which is different than other books, this book uses a more traditional order. The book that we use for the online 166 uses a different order. And there are a couple of orders that will always work. You just have to make sure you follow one of them. So this book, and the way we did it in trig, we always moved left to right is how I think of it. So left to right. So if we're on the outside of a function, if I had something like this, I'm just focusing on vertical transformations right now. If I look left to right for these vertical transformations, I have these three things going on here. Stretch, and then a shift up. So if you go left to right, it will always work. So your vertical is left to right, you do a reflection, and then you do a stretch or compression, and then you do a shift. So that's how I like to do it. Right to left works. Same thing on the inside. If the inside of the function had stuff going on like that, then in there, same thing. We go reflection, we go stretch or shrink, and for a 3 on the inside, is it a stretch or a shrink or compression? That's a compression. If it's bigger than 1 on the inside, it's a compression. And that should be my absolute value bar up there. And then there's the shift. So that's how this book will do it. Works absolutely fine. So we just go left to right. Now, what do we have to do before we actually know what our shift is in here? We graph our parent function, but what did we do in trig? What was the first thing I always said when we had the angle? We looked inside the angle. We have to do something before we actually see the shift. Like the shift here is not -1. It's not left 1. What did we do to see the shift? Yeah, the amplitude's on the outside. Amplitude is a vertical stretch or compression. So on the inside, we always did something. Factor first. We always did that. So if we want to see the shift here, we would have to factor out the -3. When we factor out the -3, we would get this expression. Right? So once we factored out the -3, we still see our reflection, we see our compression, and we see that the shift is to the right 1/3 of the unit. So factor first when you're on the inside. Factor first, and then you see your shift. So in trig, we called it the phase shift. And to see the phase shift, we always factored out that leading coefficient first. Okay. So here, number 12, we've got these two vertical transformations. We've got a reflection and then a shift. And so let's go in that order, and then it will work. So we're going to reflect. And these are vertical transformations. Maybe I'll put a VT up here to emphasize that it's vertical transformations. We're going to reflect. And a vertical reflection means reflecting through the x-axis. That's a vertical reflection. So reflect through x-axis. And then the second transformation here is a shift up of 2 units. So with vertical shifting, it's exactly what you see. But with horizontal shifting, it's opposite of what you see. All right, so let's graph our basic function. And then we can go from there. So our basic function is the absolute value function. It's the v, like that. So then we do our order. And with these two, it actually is not going to matter, I don't think. Let's check. So if we reflect and then shift up, we're going to get the absolute value function looking like we shift up 2 units, so it's going to be like that. In a lot of cases, you can get away it's not really going to matter which order, but in next class, I'll show you some examples where it definitely matters. So in this case, did it matter? Let's see. So we reflected and then shifted up. If we shifted up 2 and then reflected, it would be the same in this case. A lot of times it's the stretching and compressing combined with reflection that causes trouble. All right, so let me give you one to do. So let's do one based on the, what was he had the cubed, let's do the cubed root function. So let's suppose we have this. Let's put a multiplier in front and a reflection. But let's do that. And also in trig, did we do the horizontals first or the verticals first in trig? So didn't we usually start with the phase shift? When we were doing our graphs, we said, okay, where's the phase shift? And then we added the period. So that's the horizontal stuff. So it's best to do horizontal first and then vertical. Again, a lot of times it doesn't matter, but if you follow horizontal and then vertical, it will definitely work. Start from the inside and move out. And remember your basic function, the cubed root of x, different from the square root of x, although the right piece of it looks the same, or similar. Cubed root function looks like that, right through the origin. Cubed root function is defined for all x's, unlike the square root, which is only for non-negatives. Make sure that doesn't look like it's curling back up, going down. How many horizontal transformations are there? Yeah, just one. And there's no factoring. We don't have to deal with that. So this is just a shift left of 3. Okay, verticals. What's the first vertical transformation? Reflection. So vertical reflection, we can emphasize that it's a reflection through the x-axis if we want. If you have it under vertical, I know what you mean if you set it up this way. It's totally up to you. Some people would say reflect through, instead of writing the x-axis, they would say reflect through y equals 0, which is the x-axis. Sometimes that gets a little confusing if you're writing a y when you're reflecting through x. But okay, next vertical transformation. Stretch by 2. And then our last vertical transformation, up 1. So we're going to shift up 1. All right. So let's do one at a time. And depending on how messy things get, you may want to do them on separate graphs. It just kind of depends on how you feel about how messy your graph is. All right, so can I get... All right, we'll just draw it from scratch. All right, so let's go with red, I guess. So we're just shifting left 3. So 1, 2, 3. So it's going to be something like that. And then we're going to reflect through y equals 0. So that tail is going to go this way. That tail is going to go that way. So we're doing red for this one, and then blue for this one. And then we have to stretch by a factor of 2. So that vertical stretch is going to pull the graph vertically, both up and down, by a factor of 2. Let's not get into the details of what it really means by a factor of 2 at this moment. We can look at that next time. So that graph's going to be more like this then, if we stretch by a factor of 2. And then the very last step is that we're going to shift it up 1 unit. So 1 unit, we're going to be right here. And we're going to have this sort of vertically stretched part that way, and our vertically stretched part that way. So that will be our final graph. This will be y equals f of x. Can you see that? A little bit messy. Colored pens, get some pastel pens, light colored pens, and some dark ones. All right, we'll stop there. Take a look at the notes for next time. We're going to do more transformations. It's helpful if you look at them ahead of time just to make sure you have the order down and all that kind of stuff. We go through this algebra stuff a little fast, so help yourself out by looking ahead of time.